HIMT, Hindustan Institute of Maritime Training.
Topic is about the effect of heavy weather on a ship. It is a continuation of the other two videos. The previous one was, first one was about introduction to intact stability. Then it was about the meaning of dynamic stability. In the dynamic stability video, you should have seen the effect of area, that why area under the GZ curve is important for dynamic stability of a ship. If a ship is going out to sea, it is likely to experience rough weather, and the designer has to make the vessel capable of withstanding rough weather. In this, two things have to be specified. You have to tell what is the meaning of rough weather. You cannot just say design a ship for heavy weather. So there is a principle that a ship will be designed to withstand this kind of heavy weather. So the heavy weather will be specified. Okay. Second is, what is the meaning of surviving? That vessel should be able to withstand. That withstanding will be also told in terms of how many degrees the vessel can heel to, like, or when it is rolling, that it should not heel or roll beyond so many degrees. Like that is where the specification. So this criteria is given in intact stability code, and this heavy weather criteria is applicable to all type of ships. It will come under the name called wind and wave criteria, or it's commonly called as heavy weather criteria. The heavy weather criterion is also based on the same GZ curve. So the GZ curve for a vessel at your current loaded condition. This is the curve. So this side represents port side, for example. This side means starboard side. So it doesn't mean it is negative. It is only plotted for two different sides. One is port side, other is for starboard side. Then the first effect which is seen is the effect of effect of wind, steady wind. So for defining what is the type of weather, that how much severe weather vessel has to withstand, the pressure of the wind is mentioned. That wind will be blowing with so much of pressure. So the pressure which the vessel has to withstand or designed for is 506 Newton per meter square. That wind pressure of 506 Newton per meter square is acting on the ship. And what will be the worst direction for this wind or wave to create the maximum effect? It will be side, that means fully on your beam. So a beam weather of severe condition is looked at, and 506 Newton per meter square is equivalent to Beaufort scale 10. Weather at sea is defined normally in terms of Beaufort scale. So scale 10 is equivalent to this kind of wind pressure. So if that kind of wind is blowing steadily on a ship, what will be the effect? It's a steady wind. What will be the effect? It will produce so much of force. That force will act on the exposed area, which is above the water level. So the vessel starts going to one side. So as the vessel starts inclining to one side, the resistance of the water will come on the other side. So together it will create you will get a heeling moment this way, and you will get a righting moment this way. So when the two moments balance, the vessel will be at a steady angle. So the steady angle is being mentioned, that the vessel should not heel to an angle more than 16 degrees or 80% of deck edge immersion angle. That is the rule. I understand it. That is by exposure to steady wind alone, equivalent to Beaufort scale 10, the vessel should not heel more than 16 degrees or 80% of deck edge immersion angle. What is the meaning of deck edge immersion? This corner is touching the water. This is deck edge. This is touching the water. So to prove that the vessel will not heel more than that, the way it is done is like this. This is the GZ curve. This is the GZ curve. On the GZ curve, wind is acting like this. On the vessel, the wind is acting like this. So the pressure of the wind is P. Then the total area on which the wind is acting, that will be A. Then what will be the value of P and A? That will be the force. So that force will act on the center of this area. Then water will resist from this side. So this point is taken as the center of the lateral area, for the entire area exposed to wind. And this is the center of the water pressure, center of lateral resistance. Between these two, a lever distance will come. This lever distance is taken as Z. In this formula, it is taken as Z. So what will be PA into Z? PA is the force and Z is the lever. So you will get this, it is called a heeling moment. This will be the heeling moment. Due to this heeling moment, the ship will start inclining. Then as the vessel inclines, what will you get? You will get righting moment. When the two moments are equal, no, it will not be upright. It will be steady at that angle. So what is the formula for righting moment? Righting moment formula is always displacement into dz. So at what angle will the vessel become stable or reach a steady angle? When it will be when these two are equal. So if you write these two are equal, you will get a formula like this: PAZ equal displacement into dz. But this will be Newton meter square, and you are going to multiply by area. So this whole value will be coming in Newton meter. This one will be coming in ton meter. This is ton meter. So this will be in ton meter. So how do you turn this also to Newton meter? You have to multiply by 1000 to turn tons to kilogram, and you have to multiply by G, 9.819. So if you rewrite the whole thing, you will get this formula. the dz value will be equal to P into A into Z divided by displacement 1000 D. You get this formula there. So what is the meaning of this formula is, this is the upright condition of the vessel. Okay? Then the wind is beginning to make the vessel go to one side. As the vessel starts inclining, the righting lever will start increasing, dz value will start increasing. So when the righting lever reaches this value, right, the vessel will stop inclining, because that is the time you are generating the correct amount of righting movement. The righting movement is balancing the heeling movement. So this value is the righting lever required to steady the ship. So this value is written as, you solve this value based on 506 you will take here, area of the vessel as it is now, z of the vessel as it is now, displacement of the vessel as it is now, and then you will get a value of dz. That is written as wind heeling lever 1. It is written as LW1. That is marked off here. The meaning of this is the amount of dz which will be required to stop the vessel from heeling anymore. So you measure that value and you mark out here on the dz curve. Then you get an angle theta 0. This theta 0, this theta 0 should not be more than 16 degrees or 80% of deck immersion. This is the first rule. So what this means is that if your vessel is going out to sea and you've got a strong wind blowing on your side, right, up to this wind pressure, if you are heeling to 10 degrees, 15 degrees, you are still within the limits. Means your vessel is still certified as fulfilling the criteria. Okay? But in reality, wind alone will not come for certain. Along with the wind, waves will be there. So due to waves, the ship is going to start rolling. So the rolling effect of the ship, is explained by this part. Okay? So this theta 0 is the steady angle, and from this angle the vessel starts rolling. So it rolls this way, then it rolls the other way. It keeps rolling like this. Okay? So if it is rolling till this angle is called theta 1. Then if you calculate this area, the area which is here, okay, this area multiplied by displacement of the ship, what will that represent? No, the vessel was here, and due to rolling it came to this angle. You take this area and multiply by displacement. Displacement multiplied by area under dz curve always gives work done. Work done. So that means the amount of work which is done by the wave to incline the ship, that is this much, based on this area. Then how will it roll on the other side? The logic is that suppose you have something like a pendulum, you lift a pendulum to this side and you leave. Then pendulum at this point has got so much of potential energy, that is mgh. If you assume there is no friction, there is no loss of energy at all, how far will it go on the other side? Till the same energy is retreating. So it will go to the same height. Same way, if this area represents the work done, this area also represents the amount of energy stored. The vessel is rolled like this, it has got so much of energy. Then how far it will roll on the other side? Till the same area is covered. This is assuming there is no loss of energy. This assumption is the worst assumption. In reality, because of energy loss, it will not roll so much. But for safety, if you assume there is no loss at all, you will get the maximum angle. So, how far will it roll on the other side till the same area is covered? So, let us say if it rolls to 15 degrees this side, from upright 15 degrees this side, on the other side it may go to 20 degrees other side, because it's already healed this much. If this angle is 10 degrees, then it will heal that much more then. But the logic is not equal angle. Logic is equal area. This much area covered on one side, same area should cover on the other side. So this is the second principle. How far will it roll on this side? This depends on a lot of constructional detail. For example, if a vessel has a hull like this, will this roll more easily compared to a vessel which has got a hull like this? Which one do you think will roll more? This one, because it will not disturb the water at all. This will disturb the water much more. So how much will be the value of theta 1 depends on shape of the hull. So two vessels could have identical hydrostatic value. It could have the identical G value, Gz. But suppose there is a addition of a bill scale here. Will this vessel roll less? It will roll less. This bill scale will not make a difference to its hydrostatic particular. This vessel will roll less. So all these will make a difference to this value. In the code, a big table is given, but it is not necessary to go through the details of the table. The logic is based on construction of the vessel, based on dimensions of the vessel, this value of theta 1 will come. But always remember, the larger this angle is, what will happen to the other side? It will go that much more on the other side. So this should not be much. So without that, if a bill scale is not there and I add bill scale, I can reduce this angle. That is the principle. Okay, so there are two effects which are considered. What are the two effects? One is steady wind, and second is rolling due to wave action. Then the third effect is also considered. The third effect is called as a gust. What is the meaning of a gust? A gust is a sudden increase in wind speed. The wind speed is picking up suddenly. So, gust effect is considered that the ship is, suppose your ship is rolling like this, to wind is blowing from the starboard side, then you will be heeling more to the port side, like this will be like this, then you are rolling this way, then you roll maximum to starboard side. At that instant, the gust of wind is hitting the ship. The gust hitting the ship is like a sudden increase in its energy. Like it is similar to hitting something with a hammer. Then if you hit something with a hammer, the kinetic energy of the hammer will be transferred to the object, and that will happen suddenly, like that. You know. So similarly, we say the gust is hitting the ship. And how much will be the strength of the gust? The rule says you should plan for 50% more. That the wind pressure is increasing by 50% more due to the gust. Or it is taken this way. This is the LW1 value you calculate, add another 50% to that. So that will come out like this. If this is this much, add some more, 50% more. Then you get a line like this. So this whole distance is called as LW2, including the gust. So LW2 will be, since you are adding 50% more, LW2 will be 1.5 times LW1. In simple common sense meaning, it means the vessel is being hit by wind pressure, which is another 50% more. Then what the meaning of this? What is the meaning of this area then? The extra area. This area. This area represents the extra energy that the vessel gains because of the gust. It is like hitting with the hammer. So the total potential energy of the vessel now becomes how much? It's not only by this value, it goes up to this value. So will it incline more on the other side? Because this area will incline even more. So how far will it go on the other side? If you assume there is no loss at all, it will go till the same area is covered on the other side. It will go till here. This much area is covered, it will go to the other side. Assuming no loss. And this angle where it can reach will be called as theta 2. And the limits are put for this angle. What is this angle? This is the practical way of thinking is you are traveling on your vessel is facing rough weather, equivalent to force 10 on the Beaufort scale on the beam of the vessel. Steady wind was blowing, rolling due to wave is happening, and then you are hit by a sudden gust. And all this is coming on your starboard side. So the maximum angle for the vessel will come on the port side. That maximum angle should not exceed certain limits. 3 limits are given. What are the 3 limits? Number 1, this should not go beyond this. This angle is called theta C. If it is going beyond this, what does it mean? What is the writing lever here? At this point, the writing lever has become 0. So you should not heel so much, or you should not roll so much that the writing lever itself becomes 0. So that is the first thing. You should not cross theta C. You should still have some writing lever left so that the vessel can come back. Second is it should not exceed down flooding angle. Down flooding angle was defined, explained in the previous video also. Down flooding angle means it is the angle at which water will start entering the hull through openings which are not weather tight, which cannot be closed weather tight. So that means without a damage to the hull, there is no damage to the hull. But as the vessel inclines more and more, through openings water can come inside. That angle is called down flooding angle. So you should not cross the down flooding angle also. Third limit is theta 2 should not exceed 50 degrees. Out of these 3, whichever is the least, that must not be exceeded. So depending on the ship type, one of this will become the lowest. Imagine your ship is like a car carrier, right? A car carrier's freeboard is very high. So its deck-edge immersion angle also will be large. Right? So if a very strong wind blows, if the vessel is inclining to 15 degrees, it is still considered as fulfilling the criterion. For a ship like that, even downflooding angle may be very large. So in that case, 50 may become the lowest of the three. Then the interpretation of the rule is, if you are going up in force 10 wind weather and you are rolling to 49 degrees because of that, you cannot complain. I understand the meaning. If you complain to IMO, what will IMO say? Huh? They will say your ship is certified as fulfilling the criteria. If the criteria says 50 degrees should not be exceeded. So is a 48 degree, is it a safe limit? Then where does the practical safety comes? The practical safety of the vessel is based on this logic. The entire calculation is for weather coming on your beam. Right? Weather coming on your side. Wind is coming on your side. Waves are coming on your side. Is there anything you can do to control the speed of wind? You cannot do anything about the weather, but direction can be controlled. So if you can alter the direction such that it doesn't come on your beam, then you will not roll so much. Otherwise, vessels will roll very severely in heavy weather if it comes on the beam. That is the design limits are only like that. So when will you end up taking heavy weather on your beam? That you are not able to do anything. Like waves are coming on your side. If you steer into the waves, you will not roll so much. What will stop you from doing that? One is destination. Like destination will mean that my boat have to go here. I cannot go this way to some other place. But that is usually momentary. Sometimes you will have land on that. You cannot say that okay, I will avoid the way, so I will go on land. But more practically, the problem is losing power. That if you lose power, then there is nothing you can do. Are you understanding? Always remember this. You are all engineers, so remember this. For the vessel, the worst thing that can happen in heavy weather is losing power. That you lose your main engine, that you cannot steer the ship, then you will be in very, very deep trouble. Because vessels are not designed to take very severe weather on the beam and survive. They will not, because the angles will be very, very high. And what happens with very severe rolling? What all can go wrong? See, this kind of rolling is going to create stresses in all parts. Your cargo will shift depending on the ship type. Suppose you have the brake bulk vessel where parts are there separately. The container ship, will the containers be able to sustain the load of rolling so much? Will the lashings be able to take? All that will suffer severe damage. Will your machinery continue to operate if the ship is rolling for 40 degrees, 50 degrees? So that is what you risk. So always remember, most important heavy weather precaution is don't lose power. And the risk of losing power increases in heavy weather, because what will happen to your fuel? fuel will get contaminated. In the sense, all the sludge and everything will come. Oil levels in your sump will be a problem. Understood? So the way sailing officers have to understand heavy weather is, vessels are designed to withstand some amount of heavy weather. And the criterion is based on force 10 coming on your beam. But the limits are not very safe limits, actually. So practical safety lies in the ability to avoid getting severe weather on your beam. That means the ability to steer into the wind. But when you start doing that, vessel will start pitching. If you start going into the wind, what will happen? If the waves are coming only on your beam, the ship will roll. But if the waves are coming like this and you go like this, vessel will start pitching. Pitching will create another set of problems. Structurally, which is worse, pitching or rolling? Pitching is worse because two reasons are there. Number one is the speed will be very high. Rolling happens often gently, but pitching speed is very high. The vessel is very stiff in this direction. So stresses are high. Second, the vessel will slam. It will go out and it will hit the water again. And water will come on the deck. So structurally, pitching is very dangerous. Severe pitching. And then it also can lead to other kinds of rolling problems. So there are other types of rolling issues. This will deal with in the next video. That is called synchronous rolling. Also, there is one more type of rolling called parametric rolling. They are what happens to the vessel as it runs. So each step you will see that if a vessel is heavy, displacement is high, it will not roll so much. If it has got large area under the GZ curve, then also it will not roll so much. But there are other factors which start coming. One of them is the design of the other factors. That's what this graph shows. Third is actual wave pattern, periods of rolling, all those will also affect the actual rolling.